Hello everybody. This problem is in series with the other two videos which are made to consolidate the concepts on series parallel resistances. Without wasting much time, let us go ahead with this problem. This problem reads as, in an unbalanced bridge circuit of the figure shown below, find the potential difference that exists across the open switches. Also find the current which will flow through the switch when it is closed. The problem is written like this. This appears to be a Wheatstone bridge kind of an arrangement which has 4 arms. It has got 2 parts. The problem has 2 parts. One is the switch is kept open. When the switch is open, we are supposed to find the potential difference that occurs or appears across the switch. And second part of the problem asks you or expects you to find out the current through the switch when it is closed. So let's see how to do or how to go about this problem. Okay. To begin with, let us try to name the junctions or the nodes so that we can refer to them as and when needed. Okay. I will name the junctions. This is A, B, C and D. Okay, we will write the first part of the network. This is the problem given. So part A of the problem or part A of the problem. Okay, I'll choose my white pencil back. Okay, so the problem asks, switch condition is switch is open. Switch S is open. Alright, so we will rewrite the diagram. We will rewrite this circuit. The given circuit is rewritten. Alright, now when the switch is open, let us try to see how the current flows from positive to negative in this particular configuration. What is the course of the current? Let us try to see. Okay, if I can mark the currents by yellow for our better understanding, I'll call this current I. The current I, when it comes to the junction A, it has to go back to the negative via junction C. Alright, so in order to do so, the current at A obviously splits into 2 parts. Okay, I will call this current I1, the other current I2. Okay, the current I1 when it comes to B has to go via 12 ohm up to C, because between B and D, though there is a switch, the switch is open and current doesn't flow in an open path. So current I1 traverses via 12 ohms. So this current is also I1. Similarly, the current I2 when it comes to D will take its course via 4 ohms, and this current obviously is now I2. And I1 and I2, they combine at the junction C and goes back to the supply as I amperes. If this is understood, then the problem becomes easy. Now, when the current flows, when I1 amperes flows through 3 ohms, the same current is flowing through 12 ohms. So obviously, this network can be seen as a series combination of 3 and 12. This 3 and this 12, they are in series, because they are carrying the same current of I1 amperes. Similarly, 6 ohm resistance that is connected between A and D is in series with 4 ohm resistance which is connected between D and C, because they are carrying the same current. When two resistances carry the same current, They're supposed to be in series. It is a very, very simple fundamental which we have already learned. Alright. So now these two, the 6 ohms and 4 ohms are in series. I can even, for better understanding, let me write one more diagram. Though you may not need it, still I would rewrite this diagram like this. I'll give a different shape, that's all. The shape doesn't matter as such. I'll be little slow in writing the diagram or writing the circuit. I'll take this part, copy, then I'll paste so that I get this line. I will erase this. I'll take back my pencil, put it back, then I'll write this line. Okay, the two circuits are same. I will put the values in the second circuit. This is my 6 ohms, this is my 3 ohms. All the resistances are in ohms. I will not write ohms every time. I think that is pretty obvious. This is my switches. This is my positive, this is my negative. I have 15 volt. Alright, so I have named the terminals. Let me name the terminals here also. This is my A, this is my B, this is my D, and this is my C. Okay, should I put the currents also? Fine, let me put the currents also. And use the same color. This is the current I1. And here is the current I2. Obviously, this is the current I2. And this is the current I1. Alright. Now, we know that 6 and 4 are in series. This 6, this 4, they are in series. When they are in series, the voltage divides, 15 volts divides between these two values of 16 ohms, of 6 ohms and 4 ohms. We may have to determine what voltage appears across 6 ohm and what voltage appear across 3 ohm and 4 ohm and 12 ohm. Our interest is to determine the voltage across the 6 ohm and the voltage across 3 ohm. That is sufficient for us. We need not calculate the potential difference across 4 and 12 because we are interested in knowing the potential difference between B and D. We can travel from B to D via any path so that we get the potential difference between B and D or D and B. Alright, so we need to know the potential difference across 6 ohms and 3 ohms. How do we do? We go in for what we call as voltage division rule. Just as a side note, I will reproduce this part of the network. I'll erase it eventually, but you try to follow what I'm trying to emphasize here. See, this 6 ohm and 4 ohm, they are in series. Only I have taken this part of the circuit. 6 and 4 are in series, and there is this 15 volt appearing across this combination. Alright, 6 and 4 is carrying the same current, I2 amperes. So hence they are in series. So I will apply voltage division to determine the voltage across this 6 ohm and the voltage across this 4 ohm. Okay, I would first find out the potential difference across 6. How do I do? Without calculating the current, if at all I am interested in knowing the potential difference in any series combination, I go in for what we call as voltage division rule. How do I apply that rule? So voltage across 6 ohm can be determined as equal to the total voltage that is applied across the combination multiplied by the resistance across which you are interested in knowing the potential difference, that is 6, divided by the sum of the two resistances, that is 6 plus 4. This is how you determine. Okay. So this is 15 into 6 divided by 10, which is equal to 9 volt. Alright. So what is the potential difference across 4 ohm? Though we are not interested in this value, we'll simply compute. It is simply 15 minus 9. Total is 15. 9 volt is dropping across 6. So the remaining 15 minus 9, that is 6 volt, is dropping across 4 ohms. So I will now write these values here in the network. What I mean is, I will write the potential differences. Let me use this color. Okay, so across my 6 ohms, I will get a potential difference of 9 volt. Where do I write? I will write it here. This is my 9 volt potential difference, which is between this point and this point, that is between A and D. Across 6 ohms we are having 9 volt. Alright, and across this 4 ohm we get a potential difference of 6 volts. That is this potential difference. This is 6 volts. Alright, now I will clear this portion which I have written as a side note, because I don't require this. It can be computed simply by looking at the network. So I will erase this. Okay, I will take my white pencil back. It's like this. Okay, now what is the potential difference across A and B? If I want to do that, we apply the same logic. Because 3 and 12 are in series, 15 volt is appearing across 3 and 12. So if I want to know the potential difference across 3 ohm, I calculate it as 15 volt is the total voltage applied divided by, into the resistance across which you are interested in knowing the potential difference, divided by the sum of the two resistances which are in series, that is 3 and 12. This is 15 into 3 divided by 15. This is 3 volt. So what I mean is across this 3 ohm we get 3 volt. This voltage is 3 volt. Okay. So what is the potential difference across 12 ohm? It is so simple. 15 minus 3 we can compute. This is 12 volt. Okay. This is how we compute the potential differences across various elements. Okay. It is a very, very simple rule. Now, we are interested in knowing the potential difference across a switch. Switch is connected between B and D. Alright. So, if I want to see whether D is at a higher potential than B or B is at a higher potential than D, how do I do? Because that helps in finding out whether you are coming across a drop in potential or raise in potential. So if you have 15 volts at the positive end of this particular, at this point, if I have 15 volts, so at A is at 15 volts, plus 15. Okay, then there is going to be a drop in potential of 3 volts. So the potential at B is 15 minus 3, that is 12 volts. Similarly, the potential of D is 15 minus 9, that is 6 volt. So B is at a higher potential than D. Okay, so if you want to find out the potential difference from B to D, which is nothing but the potential difference across switch, we move from B to D. Okay, so I will write a statement now. What I write is potential difference across the switch is equal to the potential difference from B to D. Alright. Now what do? We will try to go from B to D. Alright. Now, as a best practice, it's preferable we put the polarity. I'll use a different color now. So, what I mean to say is, I1 is flowing from A to B. So, end A is positive, end B is negative. Similarly, along 6 ohms, the top end, that is positive, is at A and negative is at D. This is how polarity gets created. Okay, now in order to find this potential difference, let us move from B to D along any path. Okay, so if we go from B to A, it is potential difference across, and take white pencil back, it is potential difference from B to A, we'll go from B to A, and plus we will try to go from A to D. Potential difference from A to D. All right. Okay, you can even go from B to C, C to D. That will also give the same result. It will give the potential difference across the switch, or the potential difference between D and B. Okay, so now if we have to traverse this path, we will try to see potential difference across B and A. Potential difference across B and A. If you go from B to A, you are moving from negative to positive, or in the direction opposite to the flow of current, or you are coming across a potential rise of 3 volt. We are following a convention where potential drops are taken positive, potential gains are taken negative. So this is minus 3V, 3 volt. Okay, that is your potential difference from B to A is minus 3. Now we have come up to A. From A to D, if I go, A to D, I am going from positive to negative, or I am encountering a drop in potential. Drop in potential I am taking as positive, so this is plus 9. So this comes out to be 6 volts. All right. It is as simple as that. Okay. So, what do we write now? We write the result as the potential difference, I'll use white only, voltage across a switch, okay, voltage across the switch, yes, is 6 volts with B at a higher potential than D. All right. So what I mean to say is, it's like this. This is my D, this is my B, so it will be like this. This would be 6 volts. Or even if I don't want to write this, I can put it this way. This is positive, this is negative. This is how a potential difference of 6 volts would appear across a switch. Alright, I think it is understood. It is simple. There is nothing complicated about it. Now, the first part is over. Let's go ahead with the second part. What is the second part? State. Also find the current which will flow through the switch when it is closed. Let's see part B. Let's see part B. Okay. Now part B. Part B is, it says switch is closed. Switch, yes, is closed. So when this is closed, how much current would flow is the question. Alright, so we will copy back the network. I will copy back the network, but then if you are doing with pen and paper, you perhaps need to redraw it. Copy. I'll put back the figure. I have pasted the figure. Alright. Okay. Now what do? I will clear these quantities which I have written, because now these things would be somewhat different. What I mean is, now let me put that back. What I mean is, let me illustrate. Now we are trying to close the switch. Okay. When we close the switch, let's go back to the current distribution. Okay. Let us try to see. Now my current would start from the positive terminal. I can afford to call this total current as I ampere. That is fantastic, not a problem at all. I ampere will come to the point A. Let me call I1 current and I2 current. Now, when I1 and I2 respectively meet at B and D, to go back to C, they have an alternate path also. It can move with it can flow via the switch. And if you remember, these values 6, 3, 4, 12, though it is in the form of a Wheatstone bridge, it is in an unbalanced condition. So obviously, if we imagine a galvanometer in place of switch, it is going to show some deflection. There is going to be current through the galvanometer. It is no longer balanced. There is no null deflection. This is something you must remember. Okay. So what I am trying to say here is, current through 12 ohms cannot be I1. It can be something else, but definitely not I1. So what I do is, I will erase this I1. I'll erase these things also. Okay. I'll erase this current. I'll erase this also. This bloody eraser is little. I should have taken a smaller eraser. Okay. Okay, let me not bother too much about the aesthetic part of it. Done. Okay, so I will try to write the currents now. What currents are there? This current definitely is not I1. This you must be able to appreciate. I will call this current I3. I'll call this current I4. Okay, but you have to understand one thing. Here it's I equal to I1 plus I2, but the same I is also equal to I3 plus I4. It is something like 5 equal to 1 plus 4. 5 is also equal to 2 plus 3. I'm just giving an example. The sum of the two can result, the two combinations results in the same final result, right? Final value of 5 amperes. So you have to appreciate that in the previous case, the current was the same through 3 and 12 and 6 and 4. That's why we could conclude that they are in series. But now that this switch is being closed, the bridge is unbalanced. So we have this issue wherein the currents are different. You must be able to appreciate that. Okay, now with this idea we will go ahead. If this understanding is clear, then we can go further on. Okay, now we will try to rewrite this diagram like how we wrote this particular circuit, a reduced circuit. We will write reduced circuit or a circuit which we can comprehend. Okay, I will rewrite this circuit little slowly. You may have to have little patience when I deal with this. Okay. Now I'll take this part. It's that way easy for me. Copy, paste. I'll shoot this here. Then I'll take another paste. Okay, I will. What do? I will put it here. Okay, I'll put one more paste. I'll take it here. Okay. Now what I do is, I'm just rewriting the diagram. Okay, I'll have to do some adjustment of erasing the thing. Anyway, let me draw only. Can I do this? I think you will be able to appreciate that the two diagrams are one and the same. This is my 3, this is my 6. I have a 12 ohm here, I have a 4 ohm here. 15 volt is appearing across the combination. This obviously is 15. This is positive. Okay, I will take that yellow color so that I can put the currents. So my current are here is I am calling this current I1, this current I2, this is I3, this is I4. However, the current here is I, so is the current here. Okay, now we will name the junctions also. This is my node A, this is now node B, this is my node D, and this is my node C. Okay, I have taken these two nodes together. Okay, all right. Now that these two B and D, they are the same node. It would be proper for me to call this as I. What I mean is, the two nodes are same. You can call that point as B or D. They're together. All right. Now, how to determine our I1 and I3? Why are we interested in I1 and I3? Because we are interested in knowing the current through the switch. Current through the switch is essentially the difference between I1 and I3. This is my IS, I suffix S. So I need to somehow get this particular current I1 and also I3. Okay, if I get I1 and I3, I can come back to our figure 1. This is my figure 1, and if this is figure 2, From figure 2, I will somehow evaluate I1 and I3. Come back to figure 1. I will say where is I1, where is I3. I'll apply KCL at node at B, and I'll be able to get the current through the switch. Alright. To get the current I1 and I3, we need to know the potential difference across this A and B. What I mean is this voltage VAB should be known to me, so that if I know this potential difference, I can divide it by the resistance and I will get the current. Similarly, to get the current I3, I need to know the potential difference VBC here. This potential difference I need to know. So if I know these potential differences, then I'll be able to compute the current. Now, my objective is to get these values. Alright, so I need to know the potential differences. Let me mark those potential differences. Okay, what I mean is I need to know the potential difference here. I will call this as V3 ohms. Okay, and I will get this current also. This is my this is V3. Okay, this is V6, and this potential difference is V12, and this potential difference is V4. Okay, I'll compute these potential differences. How do I do? How do I do the potential difference? How do I compute? See, if I can see figure 2, it's very clear that 6 and 3, they are in parallel. 6 ohm resistance and this 3 ohm resistance, they are in parallel. And this 4 ohm resistance and 12 ohm resistance, they are also in parallel. So we can find out the parallel equivalent, and further on we can find out what is the potential difference. So what I mean is I'll write one more figure. This figure will be clearer. In the sense, few things will become clear. So what I mean is I'll put one resistance here and I'll put another resistance here. I'll go back to the supply. Okay, so I will this is my 15 volt, positive, negative, and what is this resistance? Now this is my 6 into 3, the parallel combination, divided by 6 plus 3. Okay, 18 by 9, 2 ohms. Alright. Similarly, this resistance is a parallel combination of 4 and 12. 4 into 12, 4 plus 12. This is nothing but 3 ohms. Let me name the junctions also, or the nodes. This is A, this is C, this point is now B or D. Alright. Now, if I need to know the potential difference across 2 ohm and 3 ohm, what do we do? This 2 ohm, 3 ohm, as we can see, they are in series. So we can easily apply the voltage division. What I mean is, in figure C, rather in figure 3, the potential difference here is going to be, I will calculate this potential difference. This is equal to 15 into 2 divided by 5. This is 6 volt. What is this voltage? I am trying to compute this potential difference. Similarly, the potential difference between this point B and C can be computed as 15 into 3 divided by 5. This is 9 volt. Okay, where we have the applied voltage to be 15 volt. 15 volt is appearing across the combination. out of which 6 volt is appearing across 2 ohm and 9 volt is appearing across 3 ohm. Alright, so we go back to the figure 2 and we will now write what is the potential difference we are having across 3 ohm. Where did we get this 3 ohm and 6 ohm? They are parallel, right, which resulted in 2 ohms. So obviously this is 6 volt. Okay, that is 6 volt. This is also 6 volt because they are in parallel. Voltage across 12 ohm, what is this equal to? This is 9 volt. And that is same as this is to be 9 volt. Okay. So we know the potential differences, we know the resistances, now we will write the current. Okay. Now, if I look at figure 3, what is the current I in figure 3? This is my I. How much is that I equal to? It is simple. From figure, let me use white color back. From figure 3, the current I is simply equal to 15 divided by this 2 and 3, they are in series, right? They are carrying the same current, that is 5 ohms. So 3 amperes is the current. Alright, whether it is figure 1, figure 2, figure 3, I is the same, that is 3 amperes. I'll put back in figure 1. This is 3 ampere. We have computed this current now. Okay, now we will compute I1 and I2. How do I compute I1 and I2? We'll go to figure 2. We will make use of figure 2. From figure 2, what is I1? The current I1 is simply the potential difference across 3 ohm, that is 6 volt, divided by the resistance 3. I equal to V by R. This is 2 ampere. Okay, I'll put it back in the figure. This is 2 ampere. Alright. Now, we will calculate current I3. So, we will again make use of the figure 2 and we will compute I3. What is I3 equal to? This is my I3, right? Where is my I3? This is my I3. Okay, what is I3 equal to? How do I do I3? I3 is simply the potential difference across 12 ohm, that is 9, divided by, this is 12. And this is 0.75, 0.75 ampere. Alright, so I'll put this value in figure 1. This is 0.75 ampere. Alright, having computed these values, now we will try to see what current would flow through the switch. It is simple. We will apply KCL at node B. Okay, we will write that statement. Applying Kirchhoff's current law at the node. What node is that? Node B. Okay, if I apply KCL at node B, I need to write I1 is the current entering node B. I1 equal to the current through the switch, that is IS, plus the current I3. They are the living currents. Okay, therefore, the current through the switch, which we have designated to IS, is simply equal to I1 minus I3. So, my I1 is 3 ampere. My I3 is 0.75 ampere. So, the difference between the two, I1 is 2. I1 is not 3, I1 is 2, isn't it? I1 is 2, I1 is 2 and I3 is 0.75. If I subtract one from the other, I will get it as 1.25 ampere. This is the current through the switch. All right. There is going to be a 1.25 ampere of current through the switch. When you close the switch, the current flows through the switch because this bridge is not balanced. Okay, so for you to have the bridge to be balanced, R1 divided by R2 equal to R3 divided by R4, or the potential difference across A and D should be equal to the potential difference across A and B. We have done one such problem. I suppose our problem 2 or problem 1 we have, I think problem 2 we have done a bridge and a balanced. So that way this problem is little different from what we have done previously. So we will write the result as a concluding statement. The current through the switch yes, is equal to 1.25 ampere and it is from right to left, or in a diagram we have called it B, from B to D. This is the direction of flow of current. Okay, the magnitude is 1.25 amperes, but the direction is from B to D. All right, little tilted line, shouldn't matter. Okay, we don't require any more decorations to be done. 1.25 amperes. Okay, the first part of the problem and the second part of the problem. First part of the problem, he talks about the potential difference across a switch. It will result in a 6-volt potential difference. When you keep the switch open, there appears to be a potential difference of 6 volts, because of which there is going to be a current, otherwise there wouldn't be any current. All right. So this completes the problem. Problems of this nature will make you understand these concepts well. You need to do more and more problems to build your concepts, build your, consolidate or your, strengthen your concepts. Only then you will be able to attempt little complicated or complex problems in network analysis. Hope this video is useful to you. Thank you, and see you with few more videos. I will try to make few as and when I get time and upload. Thank you for viewing.